So thank you very much for coming. So what is this talk about? DSLs, obviously, but it's a huge territory. So let's navigate to the corner that this talk is about. We could write the implement a full-fledged language, build our own tooling with a custom parser, type checker, and so on. The problem is we have to build these things. So that's not what this is going to be about. This is going to be about embedded DSLs, that is internal in the language, where we piggyback on the host language for syntax and parser, type checking, ideally integration with the IDE. As a trade-off, we get less freedom in defining our own syntax, or maybe not so good error messages, no custom tooling. But well, that's what we get. Now, a DSL, already a fluent syntax on top of some imperative API, can be considered a DSL. But nothing against fluent. But I really want to have my AST as a value, my program as a value. And there's an abundant and blossoming space of these embedded shallowly, meaning whenever there would be a function in the DSL, it would be a Scala function. For example, the DSL for parser combinators, or a lot of monadic DSLs with deferred evaluations. They have some operators of their own, but they also have Scala functions inside. And that's great. If that's all you need, good. They are quite easy, relatively easy to build. But sometimes you really want control over your program, over your abstract syntax tree. So we don't want functions inside our Scala functions inside our AST. What we really want is the AST to be a data structure, and that gives us possibilities for alternative interpretations. With Scala functions, the only thing you could do is to run the function. But what if you want to serialize your program or visualize it? Maybe visualize it mid-execution, do some static analysis, or generate code from your AST in a different language. All this would be relatively easy if the DSL was not very expressive, but we really want user-defined functions with some non-trivial control flow. Point-free representation is a handy way to represent such functions without using Scala functions inside. Here's for illustration. This is what we normally write in Scala. We use variables to give names to function inputs and then use them in the body. On the right is an equivalent program without or definition of functions without ever giving names to variable inputs. And this is good, but and sometimes it's even more concise than the pointful representation, but you don't want to have only that. Bigger programs get really hard for humans to read or write. So we also want our DSL to support variables. One way to achieve this would be to use quoted DSLs, where we use usual Scala syntax, including anonymous function syntax, and then use a macro to parse it and give it a different meaning. This means we have to use the metaprogramming capabilities of Scala and deal with Scala's AST, which is usually much more complex than your language that you are trying to build. And also, there are some limitations that macros do not see through some elements of the AST. Sometimes a sub-expression could be just an identifier, but you would like to see what's behind it. So I want to avoid dealing with Scala AST. So maybe we have to give up piggybacking on Scala's syntax for binding variables and do something like here. This is from the JOQ library, which is a DSL for constructing SQL statements. In SQL, the select from statement would be binding the variable a, which is then later used in the where clause. But here we have to declare it upfront and then use it both at what would be the binding side normally and then in the use side. So we're not going to do this either. So maybe we are just asking for too much, and maybe we should put some effort into developing an external DSL. But let's not give up just yet. There's a technique called deification. I did not make up this word, which, as it suggests, eliminates the lambdas or anonymous functions. So instead of, in practice, where you would normally write an anonymous function on the types that you want, you work with some auxiliary expressions. So you write a function on auxiliary expressions and build up another auxiliary expression using some syntactic conveniences of Scala, like extension methods, to give us nice syntax inside. And then what can we do with such function? As I said before, you can only run the function, then there's nothing else you can do. So how do you run this function? You create some fake expression, which would be a fresh variable, pass it to this function, and obtain, this is a fresh variable. You have a fresh variable and the body, which is an expression which inside references this variable, and return this as your AST. And this is what some libraries do. For example, the offload does this. And we have achieved the goal of having programs as data, so they are introspectable. But I have trouble with variables. Dealing with them is error-prone. You have to do substitution when you execute. You have to be careful and do a capture-avoiding substitution, so that the binding does not get binding of variables does not get mixed up, or you could have undefined variables. This is really just a string. You could have something more fancy, but if you ever going to serialize the AST, you will have something like strings inside. Substitution when executing is a non-local operation. It's not like one atomic step, and you can have these illegal programs with wrong variable binding. But we would like to make malformed programs unrepresentable. That's the mantra in functional programming. So what could we do with this? We could take one step further and get the data structure full of variables and convert it to point-free representation. We mentioned point-free before, and that we don't want our users to have to write in this style. But for internal representation, it's actually okay, and it avoids avoids these malformed programs with mixed up variable bindings. We know this is possible thanks to a well-known, I do have one, thanks to a Curry-Howard-Lambeck correspondence, which is a correspondence between various logics and various typed lambda calculi and categories. But for our purposes, we are only going to take that it is possible to take a lambda expression and function defined via lambdas and convert it to arrows of a category, and that is the point-free representation. So we get the best of both worlds. Users can use variables, and the implementer does not have to deal with them. So this is the region that I'm going to focus on. So this is our goal, restated. The user of our DSL would like to write their functions using lambdas and auxiliary variables, perhaps pattern matching. And the developer of the DSL would consume a pure data structure, which is an abstract syntax tree of the program and has no Scala functions inside. So how do we do that? I mentioned correspondence, but could we not implement it ourselves, but get it from a library, a canned off-the-shelf implementation? And I'm going to use one provided by the Libretto library. Libretto itself is a DSL for concurrency in Scala, but this delambdification is applicable to other DSLs. So in order to prove that, I'm not going to use the Libretto DSL, but a different DSL for our demo purposes, and it will be a DSL for defining workflows. What's a workflow? A Wikipedia definition: orchestrated and repeatable patterns of activity. Well, what's an activity? That will depend on the subdomain. I would just simply say it's a scripting on top of activities, and the characteristic properties are that it can be long-running, but most of the time it's waiting for some activity to complete, or say for some user input or human input, which really could take days, like respond to an email. So we cannot assume that the program stays in memory for the whole execution, and we have to support durable execution so that we can, whenever program execution is suspended, we can then pick up where we left off. Here's an example. So we would support some built-in operators. This would be branching. This would be sharing some intermediate result. There would be activities which are domain-specific and will be pluggable. And the workflows have a nested structure, so there can be sub-workflows. And we want our workflow DSL to be expressive enough with respect to the control flows it can define. So we want branching, loops, parallel processing, sharing intermediate results, which might sound obvious, but for example, the IO monad-based DSLs for concurrency struggle to express both parallel processing and sharing intermediate values at the same time without falling back to imperative concepts like spawning fibers and such. We want reasonable type safety, but we don't want to implement the type checking ourselves, so we would like to piggyback on the Scala type checking. And importantly, we want to able to execute the workflows durably. And maybe later we would also like to visualize our program, maybe the whole program, but maybe even as it's executing, perhaps do some static analysis, execution traces. And maybe when we get very invested, we would really like custom syntax and tooling. So maybe we will want to switch to an external DSL later, but so that we don't have to rewrite all workflows that we have written using Scala syntax. So far the activities have been kind of abstract. I'm going to use an example inspired by this documentation from Temporal, which is a solution for workflows as well. And it's a background check where a candidate, when they apply for a job, the HR person initiates a background check by inputting candidate email. Candidate is asked for acceptance of the background check and provide some personal identification and their employment history. And then the workflow concurrently starts an automatic check of criminal record, of civil record, and asks a research team for verifying employment history. So this will be a manual task. And when all results are collected, produce a report and pass it to the HR person. And this diagram we saw before actually corresponds to that. First, we ask candidate to accept, and if they declined, we create a report that they have declined. And if they accept, they would provide some personal ID and employment history. The personal ID would go to the left and be used for both criminal check and civil record check, and the employment history would be passed to the research team for verification. When all of the results are collected, we would create the report with the results, and the HR person would read it. Now, getting users' acceptance, we start with an email address and then create a promise that the user will respond, and we return the response. But with the completable side of the promise, we would use it to send an email to the candidate and wait for a day. And if we don't get a response, we repeat. Okay, so here's a sketch of the code of our DSL that we would like to write. We use lambdas. Input is the candidate's email address. Ask the user for acceptance, and then pattern match. If the user accepted, they would get they would provide us their personal ID and employment history, and we use those to do the checks and produce the results. Notice that we use lambdas here, we use pattern matching, we use intermediate variables, but what we return, this flow, is a pure data structure with no Scala functions inside. So this flow function has to do the magic somehow. On the other side, what the language implementer gets is a pure data structure with no Scala functions inside, which actually corresponds one-to-one to the workflow diagram. On the lowest level, individual sub-workflows or activities, but also each sub-workflow corresponds to a data structure on the left. This is the whole accepted branch. This is the whole switch, pattern matching, and the whole workflow. All right, so restating our goal, the user of our language writes using lambdas. The language implementer gets a data structure corresponding to the diagram, and we want to use a library solution to do the translation. So how would the library do that? Let's, I'll just give an idea. Let's now focus on the accepted branch, when the candidate accepted the background check. Well, there's a function inside, Scala function. What is its type? It's a function on auxiliary expressions from personal ID and employment history to generate a report. Okay, let's open the can. What do we have inside? There's this delambdify method that seems to be applied to this user provided function. So if it is applied, then we get a workflow, which is a data structure representing this program. Now, how does this delambdify do its magic? Again, it can only evaluate this function. So what can it pass into it? It creates a fresh variable and passes it to the function, and as a result gets an expression tree. This will be provided by the library as well. Maybe I'm simplifying a little bit here, because flow is not provided by the library. It's from your own DSL. So you would have to pass some evidence that flow supports some operations, but those are some really basic operations. So what would the expression tree look like for this onAccept function? It would be something like this. We can get an idea how it's constructed. So the input is a pair, which is deconstructed via overloaded extractor, like a nice feature of Scala, into the left and right side. Then sub-workflows or activities have an extension method to apply it on a sub-expression that creates these subtrees. And then pairing, there's an operation for pairing subtrees. So we pair the subtrees and pass it again via extension method to the final activity to produce the results. Okay, and this is where some solutions at delambdification stop. So now you would return, okay, the newly generated variable and an expression containing that variable. But libretto goes the extra mile to eliminate the variables. So what libretto does is, okay, eliminate variables. How does that? How can that work? So it works recursively. To eliminate a variable from just a variable, that would be an identity function. To then compose it with the left projection, it would be just the left projection. To compose it with an activity, it would be left projection and then the activity. Same goes for the other subtree. And now the bigger subtree. Okay, what can we do? We can duplicate the input because we are using the variable twice there, and then in parallel do a parallel composition of in both cases projecting and then doing the activity. But this is somewhat redundant because we duplicate the big thing and then in both cases take just the left side, so we can factor it out, and this is what actually the library does. We first project, get only the personal ID, then duplicate it, and then pass it to each activity. Okay, continuing similarly for the verification of employment history, and then again we do those in parallel, first duplicating the input, and again we duplicate unnecessarily because we can just because in the first case we project to the left, then we on the right side we project to the right, so we can just not duplicate and do a parallel composition. This is actually important in libretto, which has linear types, so it wants to avoid unnecessary, it has to avoid unnecessary duplications or ignoring variables, which is the projection is ignoring the other part, because in linearly typed system you have to use everything exactly once. And for the whole expression tree, we compose it sequentially with the activity to produce the results. I'm using this operator as an infix notation for the end-then constructor that I showed before. So far we have delambdified this part, which corresponds to this AST, which corresponds to this part of the diagram. The declined branch is just a single activity, and then how do we do the switch? That is pattern matching on the on something like either. Well, we have an easy job here actually, because if you look here, the body never mentions any variables from outside the switch, so it does not capture any external variables. All variables are introduced within. And in that case, the language implementer does not need to reach for anything else from the library. Just implement an extension method switch on the either expression. This is just our domain type for either, and call the user-defined function twice on left and right, delambdify those, use an AST constructor for the switch expression, and apply it via an extension method again to the input expression, which is here is this one. All right, so we have delambdified the switch expression. But how would we do it if the switch branches were actually capturing some external variables? So there is in the canned solution a method for that. It's actually generic for multiple branches, not just two, but we'll just use two here. And we need to give it a way how to do the pairwise branching. This would be just our switch constructor from our AST. And we also need to give it a way how to distribute those captured expressions into the left and right branch. So we would need a constructor in our AST for that. But yeah, this is really what it looks like. And it would return us all the captured expressions and a flow from the captured expression and the either or a coproduct of all the branches, in our case just two, and the output type would be the desired result type. Okay, you can look up all the nitty-gritty details in the library. And I'll not go through other control flow operators, but in the I showed before that there was a loop repeated every day to ask for user acceptance. This is how we can represent a while loop without variables. The iteration is a flow from A to A or B, and the runtime will repeat it until it eventually produces a B. And it's also applicable to recursion. We haven't used that here, or including recursive types at the domain level. It's applicable to higher order functions, including closures. We have seen capturing variables already in the switch. And it's already applicable to linearly typed DSLs, which is actually what libretto itself is. Okay, so so far we have given our users a nice syntax to write their DSL code, and we have sketched how it can be translated to a point-free representation without any Scala functions inside. But that's really only half the story. Like, what do we now do with that representation? And I was talking about durable execution of these workflows. So how could we do that? The key is that our program is data at all times, in the beginning, but also during execution. We have full control of the program. So here's how we could proceed. This is our original program, or part of it, and it starts by providing some input. Now, input is data, so that's serializable. We can persist it. And our program is also data, as we have just shown, so we can persist it as well. And now we will step through the execution. So we pass the input, and we see there's branching. So we check on the input whether it's going to the left or right. We found out it's going to the right. And this is our new state. So we have done a very small step. We still have available input as data, and the continuation of the program is still data. So we can persist this state. Okay, we continue. We find out that the input is actually a pair. So we split it into the respective components. And this is our new state. Our available input is still data, so we can persist it. And the rest of the program, guess what, is still just data. Okay, let's continue. We learned that we need to duplicate one of the inputs. So we do. And that's our new state. Still just data and persistable. Okay, now it becomes interesting. So we have reached an activity, which is something that can fail in or take a long time. In this case, this was the checking the criminal record. So what do? We start the activity on some worker, let's say, and we create a durable promise that will be completed when the activity completes. And also the activity, the recipe for the activity is just data, so we remember that in case we want to ever retry and put the reference to the promise into our current state of the workflow. So our inputs are either available inputs or references to some durable store which is still data. All the inputs are still data, and the continuation is still data. Let's say we started the second activity as well, and then let's say the first one completed, so we can bring the result to the input of our program, clear the activity from in progress activities, and continue. Now, we would like to have a property that whenever there's something available in our inputs, we can make progress, but we cannot really make progress now because this activity needs 3 inputs and we only have 1 available. But anyway, we remember that we partially apply the activity, so to the available input we need a slightly more sophisticated representation to store that. Libretto actually provides some usable data structures for that, and we have reduced our inputs, which are still data, and the continuation is still data. So, and we repeat this until the workflow completes. Okay, so the key was that the execution state was always just data, which is introspectable, and so it opens new possibilities. In addition to just execution, we could visualize it even mid-execution. I draw those diagrams manually, but you could generate them. Maybe you would want editing them mid-execution, and that would be doable too. And I have omitted a lot of details when it comes to workflows, for example, serialization, especially of your custom data types, like those reports or email addresses or employment history, that those have to be pluggable. But that's all doable, just not the focus of this talk. How this stuff is actually persisted. Maybe we could store a workflow as a graph, or maybe just as a single document, which we load and store fully at each step. And how this thing actually runs, like coordinator and workers and dispatching and scheduling. And the promises that are created, for example, when we send an email and expect a response, how would these promises be completed from the outside world? So I'm not trying to trivialize these things. These all take a lot of work, but I was focusing on the language aspect. Let's recap some Scala features that were used with advantage for this DSL. Extension methods. Whenever we applied an existing workflow or an activity to an expression, that was an extension method apply that creates a new expression, or that switch statement was an extension method. Extractors, very useful. We can have custom pattern matches on those auxiliary expressions. Context functions. I lied to you a bit about the signature of the delambdify method. It actually, the function you pass in actually takes an implicit lambda context that stores some information about the variables, but it was not in the user's face thanks to context functions. Givens, those we haven't seen them explicitly, but they are used a lot. Exper, our auxiliary expression, actually comes from the library, but you would expose it probably to your users as an opaque type. We have seen a polymorphic function, and this solution is not dependent on macros at all, but we can use them to get, for example, source positions of those auxiliary variables for error messages. So a very lightweight use of macros. And also the library uses path-dependent types a lot, which we haven't seen here. So although the idea of delambdification and conversion to point free is applicable in any language, these Scala features make it especially pleasant in Scala. All right, so let's sum up some takeaways. Programs as data give us new possibilities. So for example, for the workflow use case, a solution where you write workflows, the control flow using your general purpose programming language does not give you the control that you get from programs as data. For example, that visualization. And we have seen that it does not actually take much to represent expressive control flows like loops or branching. My takeaway is also that variables are problematic, dealing with variables, but we can avoid them in the internal representation without taking them away from the users. And hopefully the translation is somewhat affordable thanks to a library solution. And perhaps I have expanded your view of what could be implemented internally within Scala as opposed to having to implement an external DSL. Well, so with that, thank you very much, and I'm open to your questions.